Hey guys, so I'll be doing number one, and number one says that show that each of the following statements are false, okay? And we're given the option to do this graphically, so it might be easier. So A says that if f of a does not exist, then the limit as x approaches a of f of x does not exist. So, since we can do this graphically, let's start drawing by our x and y plane, okay? So over here it says that f of a, which is a value, so a, we have a point A, and it says it does not exist. This means that there will be an open circle where it is defined. Then it says that the limit as x approaches a of f of x does not exist. So the definition of limit says that for a limit to exist, as x approaches a certain value, all points from the right and left side must equal the same value, or at least approach the same value. This means that it doesn't matter what it's looking like anywhere else, the limit should come down to this one value. Okay, this means that from the right side it's approaching this value, A, and then from the left side is also approaching this value of A. Okay, it doesn't matter what this is, it could be anything, Y. Okay, so yeah, over here it says that the limit from the right and left side does not exist, but we can see that from the left side it is approaching one value, okay, the same value that where A is defined, and the same from the right side. This means that the limit does exist, so this is false, okay? So now let's move on to B. B says if f of a equals L and limit as x approaches a of f of x equals L, so we have to prove that is false. Alright, so let's start by drawing our x and y plane. Okay, so f of a equals L. So here we have an x and a y value. So we have an A and then we have an L, which means we have a point right there. Okay, and then it says the limit as x approaches A, f of x equals L. So from the definition of limits, we know that all the x values that are approaching A, which is right here, it can be like this or like that, right? So in this case, from the left and right side, the limit is approaching this value, okay? But we can have another case where, let's say, A is defined at L, right? So it's defined right here, right? And then the limit from the left side goes there. But we can also have an open circle here, and this limit from the right side goes somewhere else. So this proves that f of x will not always equal A, because the limits are approaching two different values from both sides. Now we'll move on to C. Okay? C says if f of a exists and the limit as x approaches a of f of x exists, then f of a equals the limit as x approaches A. Alright, so again, we will do this graphically. So we have our x and y plane. So they give us that f of a exists. So at A, some point exists, right? Then it says the limit as x approaches A, f of x exists. So one way we can draw this is that just because it's defined over here doesn't mean the limit has to approach this value. Let's call it L, okay? Also, one other thing we can do is have an open circle right here, right? And then from the right side and left side, the limit is approaching A at some value, okay? This doesn't necessarily have to mean that A is defined over here, even though it's defined over here. So it says that f of a exists right here, and f of a does exist. The limit as x approaches a of f of a exists. We got that right. From the right and left side is approaching one value, so the limit does exist. However, over here it says f of a equals the limit as x approaches a of f of x. So they're saying that this value, whatever it may be, equals this, but graphically we can clearly see that these are two different values, which makes this statement false.
So we're doing number 2 of our project problem, and we have to draw a graph that follows this list of rules. And looking at letter A, the domain of f has to be autonomous, so we'll come back to that at the end to make sure that it follows that. Looking at letter B, as x is approaching the negative infinity, it's going positive, right? So that's why this is going up. And looking at letter C, as the f of -3 equals 0, so that's why there's a closed circle over here defining -3. And the limit as x approaches -3, that little negative on top of 3 means it's approaching from the left side. And that would be equaling 0. That's why this connects to this point down here. And the limit as x approaches -3 does not exist, meaning there's a jump in our limit. So this could be any value. It's just it cannot connect because it doesn't exist. Looking at letter D, as x approaches 0, the limit exists, so the limit would connect on a point, but the limit on f of x does not equal f of 0, meaning there's a gap, and the f of 0 is a different point than where the limit connects.
Okay, so for E, as you can see, the limit of f of x as x approaches 2 exists. So from both sides, the graph has to approach negative infinity as x goes to 2. And then we'll come back to the vertical asymptote when we look at the domain later. For f, when x equals 5, y has to equal -2. And as you can see, the limit of as x approaches 5 from the right side, as you can see from this positive, has to equal -2. So coming from the right side, it equals -2. However, the limit doesn't exist. If you remember the definition of limits, for a limit to exist, a point has to be approached from both sides. So from the left side, a different point has to be approached because the right side approaches -2. So to make the limit not exist, this can't equal -2. It can be any point except for -2. And for G, as x approaches positive infinity, so as x value goes right, y cannot go positive, it can't go negative, and the limit also just doesn't exist. So in order to make this true, we have to have an infinite oscillation. And the reason why this makes that true is because instead of the limit approaching 1 point, it stays and oscillates in between 2 points wherever on the graph. And looking back at the domain, you can see that for every open circle, there's always a closed circle to show that all points are included in the domain, as well as there is a point on the vertical asymptote to satisfy the whole domain being present.
All right, so I have number 3 for our project problem. This is a piecewise function. So we have to solve for a and b in this problem, and it's given to us that the limit of f of x as x approaches -2, and the limit as x approaches 2 of f of x both exist. So we are given one y value here when -2 is less than or equal to x, which is less than 2. So this can be rewritten as when x is greater than or equal to -2, then the y value is 9. And when x is less than 2, y is also 9. This can be the same thing as the limits as well, because if x is less than 2 and 2 is on a number line, that means we're looking at all the values to the left of 2. So this is the same thing as saying the limit of x, when x approaches 2 from the left with a negative sign, equals 9. And Same thing up here. So if we're on -2 and x is greater than -2, that's all the numbers to the right of -2. So the limit as x approaches -2 from the right, positive sign of f of x, also equals 9. So since we know these two, and we know that both these limits have to exist, from our definition of the limits, we know from the left and the right side, both have to approach 9. So now what we can do, we go back up to this problem here where this conditional on x being less than -2. So we plug in -2 for x into this top equation. We plug in 2 for x in this bottom equation, and we know that these two equations are both equal to 9. Because this equation is basically saying the limit as x approaches -2 from the left is equal to this. -2 from the left of f of x is equal to this equation where we plug in -2 for x and this equation equals 9. So what we'll do is we'll get a and b on one side of the equation and our constant on the other side of the equation, and then we'll set up a system of equations and solve by elimination. So simplifying this out, this will become 4a plus or minus 6b minus 7 equals 9, which simplifies to 4a minus 6b equals 16. So this equation is as simplified as it needs to be right now. And then we'll go over to our last equation here, where we'll plug in 2 for x in the bottom equation. And this equation is the same thing as saying that the limit as x approaches 2 from the right is equal to this equation, which is equal to 9 as well. So the limit as x approaches 2 from the right, f of x is equal to this equation, substituting x for 2, and this is also equal to 9. Simplifying this out, we get 4a minus b all over 2 equals 9. Now to get rid of the 2, we multiply by 2 on both sides, and we're left with 4a minus b equals 18. So now we have our two equations, and then we'll set up a system of equations and solve by elimination. Alright, so I'm going to multiply the bottom by -1 to get our a's to cancel out. So I put -4a plus b equals -18. And we have our 4a minus 6b equals 16. These cancel. A positive b minus 6b would be -5b. A -18 plus 16 would be 2. Would be -2. Divided by -5, our b term is equal to 2/5. Now we will plug in 2/5 into whatever equation we choose to solve for a. So I'll choose the top one. So it'll be 4a minus 6 times 2/5 equals 16. Simplifying will be 4a minus 12 over 5 equals 16. Add the 12/5 over, and 16 over 5 will become 80 over 5. Plus the 12 over 5 where we get 4a equals 92 over 5. Divide each side by 4. We have a equals 92 over 5. And then using the reciprocal of this fraction down here, 1 over 4, where we get a equals 92 over 20. And simplifying that down further, it simplifies to 23 over 5. So our two answers are A for 23 over 5 and B as 2 over 5.